All right, cool. So we'll start with, this is all kinetics stuff. And I promise you it's not that bad. Kinetics is regulated in a few different ways, and the way we use those ways is really important when it comes to biochemical processes later on that we care a lot more about. The easiest way to regulate something is the amount of substrate that you have. If you don't have enough stuff to build things out of, well, then you're not going to build anything. Or if you don't have enough rocks to break down, you're never going to break down the rock. I mean, that's pretty simple. Now, let's say in this world you have an unlimited amount of plastic or rock or whatever the hell you're doing, and now you have to worry about the amount of machines that you have, right? Let's say I got 40 molds. Well, 40 molds is going to go a lot slower than 140, right? That's just easy peasy. And the last part of that is how fast they work. Let's say it takes 10 seconds to do it, and I have 40 that take 10 seconds, and I have 40 that take 5 seconds. The 40 that take 5 seconds are going to go way faster than the 40 that take 10 seconds. Those are the three ways in a very simplistic way that we regulate kinetics. So the first is by substrate availability. The second is by copies of enzymes, or like amount of enzymes. And the third is by regulation of those enzymes, either allosterically or covalently, so the modification of those enzymes. Cool. Cool. So in the perfect world that we live in, most of the time, our substrate availability is pretty high, just because that's how people work. If you're always fighting to get a high enough substrate, then you'd be screwed. So that would suck. Over here, he has an activation energy graph. This is just showing like reactants to products. It takes, you guys know how to read these? Have you seen these before? Okay, so it's like, this is the amount of energy that you have starting with between, let's say, two reactants, and when you put them together, you're up here. So you have a higher amount of energy. But to get there, you need to hit the activation, or the amount of energy that it requires to put those two together. Vice versa, if it was backwards, you'd go products to reactants, and you'd still need to hit that high amount, but it's easier to get there. So what enzymes do is they change the activation energy. They either raise it or lower the activation energy. If they were to lower the activation energy, then the reaction will proceed faster. If they were to raise the activation energy, then the reaction will go much slower. People like describing it as a hill. If I'm pushing a ball up this hill, and then I was to lower the hill, well, that'd be a lot easier. Versus if I was to make this hill into a mountain, it would be much more difficult to get the ball up atop that hill and over. That's the whole point of enzymes, is just change that activation energy. Cool. Can we reach the activation energy without using anything? Absolutely. That's something that people tend to get stuck on or a little confused on. Things happen spontaneously, right? What's a good one I can think of? Nothing's really coming to me off the top of my head. Not gonna lie. Sorry, I was gonna say ATP, but you kind of used it pretty fast. ATP is pretty unstable, so it will spontaneously just break off and become ADP. That sucks. You put a lot of energy into making that, but who cares? So it can happen very spontaneously. Another thing that can happen spontaneously is isomerization, which is like changing a square into a rectangle. It's the same exact thing. It just changed a little bit, the order. Cool. Other things do require energy, and those are what's going to be most important to us later down the line, especially when you guys get to glycolysis and stuff. Those are rate determining steps, and that's what he's kind of getting on over here, where he's talking about this complex being reversible, but this one being irreversible. You're going from a large one thing to two small things. Yeah? It's like putting two Legos together versus taking two Legos apart. That's the whole idea. Cool. The equations get to be kind of a pain in the ass. As long as you guys can understand what they're saying, you should be fine. But getting to understanding what they're saying kind of sucks. So let's go through it. Vmax, which is the velocity of which the reaction takes place. So let's say its Vmax is 5 seconds, or 5 products per second, right? That's the fastest it can go under the perfect conditions possible. It's dependent on the Kr, which is, it's kind of like a constant in a way, something that isn't really going to change, while E total is the amount of enzymes that you have. Does that make sense? So you can go as fast as you can based off how many copies of the machine you have, and Kr, which is regulated by structural changes, effects on the activation energy, which is kind of related to the activation energy graph that he has over there. Do case 1. What the hell is that? I think the low floating the high.
Compare high affinity
Just
to
compare
low
high
affinity to low.
Oh, I don't even know how the hell you read it. Compare high affinity to low affinity. High affinity is a low Km. Okay, so it's Km is more like the reactions that the enzyme have with the substrate. You can think about it like this room, for example. If I was to have all of us in here and everyone needs to go high five someone, it's pretty likely that we'll be able to do so quite easily. That's first the interaction between the substrate and the enzyme. So it's important that they first interact. The second part of that is it is important that they interact in the correct orientation. If Cami was facing the opposite way and I went to go high five her, it would not happen, right? Because she's facing the opposite direction. It's not going to happen. Or let's say if I was way up here and she was way down there, all of the above, right? So the orientation matters just as much as the interaction matters. So those are kind of the two big parts of that. And how do we get that? We get it based off the concentration of the substrate and how it's like the probability of getting them together. Cool? So if the probability is really high, then we're going to be able to go very fast. But the probability of them coming together is really low, then we're going to go much slower. Does this make sense to y'all? If not, we can go through it one more time, but better.
Say it one more time.
Sure. So my max speed is dependent on A, the number of copies that I have of the enzyme, or the working thing, and B, the probability of the interactions between my substrate and my enzyme, A, hooking up together, and B, being in the correct orientation. So the first half of that, hooking up together, is that if we were all in this room, the likelihood of me going together is really easy, But if we were all in the state of California, it'd be much harder because the probability of us interacting is much lower. The second half of that is the probability of us interacting in the correct orientation. Because remember, everything is in a three-dimensional space. So even if you have the right puzzle piece, it needs to go in the right spot. Yeah? Cool. Now the two of those together, plus the amount total that you have of these copies, dictate how fast you're going to go. The higher the probability of us working out together, the higher or the faster that it will continue to run. The lower probability of us working out together, the slower it will run. Cool. Now, in a perfect world, where we're a match 100% of the time, and I'm always interacting with you, is going to be my Vmax. But am I ever going to get to that point? No. Cool, so that's with the full saturation of substrate. So I have 100,000 when I do 5 a second, right? And that 100,000 never drops below 90,000. Does that make sense? I have so much that I can use, I'm never gonna be able to use all of it. Cool. If that checks out, we can move towards some regulation stuff. But if not, like, hit me with it. It doesn't help me to just lecture.
And then can you explain high affinity to low affinity regarding the...
This one?
Yes.
Sure. So my Km is the probability thing. So it's the combination of those two probabilities, orientation and interaction. So if I have a higher probability of this positive orientation and this positive interaction, then it can make the complex, which is the substrate with the enzyme, and proceed with the reaction to make the product. Cool. So if I have a much higher probability of it working out correctly, then I'm going to produce more stuff faster. Cool? Okay, over here, don't worry about this. This gets important, but let's not worry about it yet. Okay, yeah, let's worry about it. Okay, so what he has here is 3 different types of, he has the same enzyme in 3 different orientations. So it's when you're like 70% of the time, when you're like 50%, and when you're 100%. So most of the time we're probably running at what, 70? I mean, here I'm hoping for a 70 in most of my fucking classes. Just fuck that shit, dude. But you picking up what I'm putting down, like our running is like a 70, like passing, right? So that's without any sort of interaction of outside forces. It's just me with my orientation and my interaction going for it, right? And based on how much stuff I have to work with, I'm staying on this black line in the center here. So good? So far so good? Cool. Now, my friend comes into my life is James. James is a terrible influence. James is telling me to quit doing whatever I'm doing, quit studying, and go fuck around and play pool or whatever, right? Now, James is lowering my ability to, let's say, 50%. So he's inhibiting me in some manner, right? So what's going to happen is my Vmax is going to drop, or the highest that I can work as long as James is there is much less than my ability if James was not there. Cool? And that's going to be on this blue line here, depending on the concentration of my substrate, right? Now, finally, Cami is here, and Cami gets me fucking studying, right? Cami says, quit horsing around, quit doing whatever the hell you're doing, and hit the books.
Lock the fuck in.
Yeah, tells me to lock the fuck in, right? She comes by and she gives me some caffeine, and all of a sudden I'm cooking with Crisco, I'm ready to go. Now, Cami puts me at like 100%. So that's going to be this red line. So now my Vmax is higher because I have a stimulator or someone that's stimulating, and at a lower concentration, I'm working at a higher speed than I would based on either of these two or without Cami. Cool. Now, did those two make sense to y'all? Cool. Awesome. And the other half of that is, let's say there's 100 me's and 10 Camis and 50 Jameses, right? You see how it starts to get complicated based on the number of copies that I am, plus how much is being inhibited and how much is being stimulated. That's kind of the important part to see, which you can't really dictate on a table like this. Coolio.
2 James is too many James.
You're telling
1
me,
James
dude.
is too many James.
Okay, if that makes sense, that's kind of a good spot for you guys to understand what's going on in terms of kinetics, right? I could say, if I'm going to increase my interactions, does the probability increase or decrease? Increase, right? Because I'm changing my interactions to be more, right? So if I have more interactions, it's more likely that it's going to work out. Cool? Now, if I were to increase the number of interactions I have with a substrate, would my speed increase or decrease? My speed would increase, because my speed is based off of the probability of my interactions and orientations and the amount of me's total, right? So if I increase either of these, then my speed is going to go up, and if I increase the number of copies, then my speed is going to go up as well. Now, here's kind of a thinker. If I was to increase the amount of interactions, the probability of orientation remains the same, but I was to lower the amount of copies, what would happen to the speed?
Wait, repeat the question.
Yeah, but say that again.
Yeah. I'll write it so you guys can see it too. I'm going to partially erase this. Oh, you're right. So let's say I increase the interactions. Probability remains the same, so I can, orientation, yeah. And I was to decrease copies. What would happen to the speed?
Oh, increase.
Wait, by copies, is that like, do you start with 1 copy though? Because we need something to interact with, right?
Good question. Let's say we start with 10 copies and I lower it to 5.
Decrease. Decrease, but why?
So decreases.
I take back my increase.
Okay. Okay, so we do decrease. Okay, let's break it down. My, whatever. My Vmax is equal to my Kr times my E total. What is really my Kr? Two things, right? It's my orientations and my interactions. Cool? So, out of these two, this one is going to be much stronger in terms of its effect on the Vmax, because Kr is technically two things, right? Cool. That's kind of the biggie of that. So if he was to ask, like, oh, what's more important, the interactions and interactions of the substrate, or the amount of copies that you have? It's the copies, right? If he was to say, what would affect the speed of the reaction more? The orientation or the amount of copies that you have? You would say the amount of copies. Because your copies is worth like a half, and each of these is worth not as much. Each of these together make the other half, right?
So your total energy depends on how many copies you have.
It's based on your speed is what we're finding. So the speed of the reaction is based on one and two separate things, right? The first thing splits into two categories. The interactions that it has with its substrate and the orientation of those interactions. If I was to have two people facing each other, then they're in the proper orientation. If they were faced opposite of each other, then they're in the wrong orientation. But to know if the orientation is correct, you have to have the interaction. Does that part make sense? Cool. Now, the other half of that is the person that's watching, right? Or facilitating, or however you want to say it. Let's say I take two of you and I randomly put you together. Are you facing the same direction? Maybe. Are you both interacting? Yes, because I did it, so the amount of me's that are there dictates how fast it's going to go. Does that check out? Cool. Any other questions on that stuff? Would it be better if I drew something out, or? This is a very, very important, like, foundational thing. If you can understand this, then when you get to the rest of the stuff, then you're sitting kind of pretty. Because it'll be easier for you to understand the following stuff. But if this is difficult, then you kind of have to play catch up when you get to the more advanced topics, if you will. I'm not 100% certain if you do it in Biochem 1, but there's the bifunctional enzyme, which is covalently and allosterically regulated, which is like a really super duper big deal. It's like one of the biggest ones. And since it's bifunctional, you don't have to worry about the number of copies total. So you only have to worry about this. But to do that, you have to, you know what I mean? So that's kind of why. If I have a ton of people around and they were to come together, this is the wrong orientation. But if they were to come together, like, that's the correct orientation. For them to even worry about that, they're all walking around. If there's only 3 people, the likelihood of an interaction is pretty low. But if I was to have you're flooded with people, the interaction is much higher, right? So now I'm gonna have a shit ton of people, so a lot of interactions, which hopefully are in the correct orientation. Now I need to look at the people in orientation, and let's say I have to put like a box around them or whatever. That would be like my enzyme. So if I have 6 boxes, then I can only do 6 pairs at a time. If I have 1 box, I can only do 1 pair at a time. And these interactions don't last forever. So would a box work here? No, because they're in the incorrect orientation. But would it work over here? Yes. So if I have 6 of them, then it can work at that pace. But if I was to have 1 of them, it can only work at a much slower pace. So then the interactions and orientation doesn't matter as much because my 1 is already being used. So that's why the total copies is more important. So Okay, what else did he go over? What questions about what do you guys have?
Wait, so just to clarify?
Yeah.
In the equation, E total is the number of copies we have, like the number of total enzymes we have.
That's correct.
Okay.
And then how would I change the number of copies? Through genetic regulation.
When it's saying like low affinity, high affinity, what exactly is that about, based on? Like the affinity side more than just the high KM?
Probably like the affinity for binding. Compare high affinity to low affinity interaction. Oh, whoops, that's what I drew. Low affinity is a high cam saturation. It's probably the affinity of the enzyme to bind with the substrates or substrate, right? He put prime to represent high KM, which would be low affinity. Just kind of funky. It's a little confusing to me how he wrote this. If I was to try and give you an explanation, I would say that something that binds heavier takes a longer time for it to release, while something that binds a little bit weaker releases quicker, allowing you to go faster. That would be my best guess as to what he was trying to get across here.
Oh, thank you.
So what else did he go over?
Pretty much just this.
Just this stuff?
He talked like very briefly about this morning some of the heme stuff, but it was like for 2 seconds, then he moved on to this.
Okay. Do you guys have any questions about anything else that he's talking about, or any of this? Like, if this is all he's gone over, I don't really know where to go from here, is what I'm kind of saying. Yeah.
Can you give us like practice questions again?
For this kind of stuff?
Yeah, anything.
I mean, off the top of my head, I honestly have no idea. It's really foundational. So it's kind of like, can I quiz you on your numbers? You know what I mean? It's like, well, what comes after 3? And it's like, I'm sure you guys all know that. So I don't think any question that I can currently ask you would be of any help to you. Do you stand up?
I was gonna say, do you wanna go over like some of the heme stuff?
Sure. I'm a resource to you guys, not the other way around. So if you guys want me to go through something, I'm more than happy to. You just gotta tell me. Because I don't give a shit. It's not like I'm doing anything.
What did you go over last week?
I can't tell you. Whatever hemoglobin.
For kind of the stuff that, right,
Probably
like all the.
peep the video from last time. I didn't watch it.
Will do. You didn't say like and subscribe.
I didn't.
Smash that like button.
Smash that
I need like a cool intro.
Bro.
What's up, guys?
No, thank you.
Snack box.
Could you show the dissociation curve again?
Yeah. I'm going to erase this half. Cool?
Oh, yes, sorry.
Shut up. I'm scared.
I'm gonna look up the one that he uses. Here we go. So while I'm doing this, how many oxygens can hemoglobin hold? 4. Yep. I feel like I should have more questions.
Multitask.
It is freaking difficult to multitask too.
It's the end of the day, it's 5:30.
5:30.
Yes.
That's it.
Oh, what was that, 100? Looked like Leo.
Yeah,
No, we put
I drew it real shitty.
Sorry, ignore me. No. I'm slow today, you guys. My flight got delayed hella last night.
Your flight.
Oh, Leo.
You just came back?
Yeah.
Who's Leo?
Well, you said Leo. I was trying to think of that to tell Cindy and I couldn't think of it. Like the same Cracker Barrel. Dutch Crunch. There we go. I was close. Stop.
every week.
No, I forgot. I couldn't figure it out. I kept saying Cracker Barrel.
Okay. I guess I can label this. Jesus, dude. Okay, hemoglobin. So this graph, the oxygen hemoglobin dissociation curve, represents all of the hemoglobin. That amount is astronomical and you don't have to worry about it. But just know that it is a very large number, right? On the bottom, I have my partial pressure of oxygen in milligrams of mercury. On the other side, I have my percent association. My percent association is the percent of saturation of my hemoglobin. So 100% would be 4 oxygens on my hemoglobin of all of my hemoglobins. Q. Awesome. Now, if you notice, I labeled venous and arterial blood. They're dictated by what partial pressure of oxygen they are at. What's important to know about this graph is that the partial pressure dictates the percent association, not the other way around. Cool? That's really important to know. The percent associate, or sorry, oh, Jesus Christ. The partial pressure of oxygen dictates the percent association. Cool. Now, let's read this. Do we all know what partial pressures are? Yep, all right, sweet. Now, starting with our kind of atmospheric partial pressure, it's a little bit more over here of oxygen. When oxygen enters our lungs, yada yada, diffusion, awesome. And it's gonna make our arterial blood around, let's say 90, 95, somewhere in there between 90 and 100 of millimeters mercury. At that partial pressure in our arterial blood, our percent association of hemoglobin is going to be 100%. Cool? Now, if you watch as the partial pressure starts to drop, does our percent association change? Not really drastically. Even when I get to my venous blood, which is the lowest partial pressure that we will have at around 40, the percent association is still somewhere between 70, 80%. Cool? That is extremely important to notice, right? If it's at 75%, that means 3 of the 4 oxygens are present on the hemoglobin. Or alternatively, somehow the percent association is 75%. Now that is still really, really high. So if I were to drop in altitude, drop in partial pressure, which would be an increase in altitude, to much lower, then you can see it instantly really start to drop off hard. That's why we don't go up super high without any sort of respiratory equipment, right? The drop off is very sharp, it's very quick, and it's very, very dangerous. We love this range. This range is awesome, it barely changes, so we're gonna always have oxygen. So even when our tissues are in a highly metabolically active state, and we're releasing more and more and more oxygen to those hungry tissues, it's still remaining at a very high and almost constant level, which allows us to not have to worry as much. Cool. Any questions so far? Alrighty. Yeah, if I were to say what dictates what, the partial pressure or the percent association, you would all say the partial pressure. All right, awesome, good job. Cool. Myoglobin looks a little bit different, and we can draw that on here as well. Just let me make sure I have the number right. Does this work? Yeah, no. Is it MG? No, it's MB. Cool. Okay, so this orange line is going to dictate our percent association of our myoglobin. If you notice, well, actually, where is myoglobin found? Muscles, yep. Only in our muscles, it's not in our blood. If you notice, our myoglobin stays like with this high percent association for much longer, right? Because our muscles are going to need the oxygen more than our blood, so it's going to be stronger and pull it away. It's kind of like the big deal behind that. Secondly, if you notice that as the partial pressure drops much past that of our hemoglobin, it still remains at a high association for much longer. This is really important because the partial pressure of our muscles are going to be very variable. They change very easily. If you guys remember, I was talking about like a cup of water versus the ocean. If you were to drop the food coloring in one, the cup of water is going to change much rapidly while the ocean is going to take quite a bit. It's the same kind of idea, right? Our muscles are much smaller than our blood volume, which means that it can only hold a certain amount. So as that amount starts to decrease, it decreases at a much higher rate of change than it does in our blood. Cool. And that's important because if our myoglobin was at, let's say, a partial pressure of 26, it still is going to remain pretty highly associated because it's still going to steal from our hemoglobin, allowing our muscles to continue to work. Any questions on that? Okay. Cool. So now what? Y'all can go home, man. Go sleep, do whatever.
Okay, well, yeah. Thanks.
I feel like once he releases what's gonna be on the exam, we'll have more to ask you, but right
Sure.
now.
Yeah.
He also just yapped about the same thing for
You got,
All of our time.
you got like an idea of what we need to know for like fibrous protein?
Whoa.
That's-
Fibers, proteins.
That's what they say, right?
Collagen and elastin and that kind of stuff.
glycine.
You still remember, huh? Collagen is 1/3. Glycine, yeah. That was it a question on your exam, Kiani? Yeah. So he's used that question every single time, as far as I'm aware. Collagen is 1/3 glycine, right? The fibrous proteins is going to be. Have you guys gotten to it yet? Yeah? Okay, we can go over some of that stuff if you want. Fibrous proteins is related to the orientation that they're in. So, gosh, I haven't looked at it in a minute, but it's like our collagen, pretty sure it's our collagen, is arranged into triple alpha helices. Which would kind of, okay, I kind of killed that shit, not gonna lie. But it's arranged into these triple helical structures, which are arranged into units, and then these units are orientated inside other units with this overlapping kind of pattern, specifically with bonds here and here and here and here, connecting the two units together, connecting all of them together, making a super duper strong thing. Why is it important? Well, if one of these little tiny ones gets fucked up, the whole thing doesn't get fucked up. If you were to remove one of these, who cares? Just put a new one in there. Glycine. I'd have to look over it. So if you guys want to do that, we totally can, but I will need a minute to go through my stuff on it. Up to you. Yeah, let's do it. Okay. Okay, you guys ready? Let's do it. So collagen is really important. You have type 1, 2, 3, 4, so on and so forth, right? You have a shit ton of different collagen, and your collagen is extremely important. What does your collagen look like? Your collagen is what I drew over here, those 3 overlapping alpha helices. Easy peasy, right? Okay, so what makes up collagen? Collagen is 1/3 glycine. Collagen's 1/3 glycine. Collagen's 1/3 glycine. Hear it as many different ways as you want, just remember it. The other half of that, or the other 2/3 of that, can be lysine, it can be proline, it can be other things. Lysine and proline is what I'm going to focus on here because those are what's really important. Over on this side, I have a proline. This is a proline in my chain, right? Over here and over here, I'm just dictating that it's one part of a very large chain. If I was to look at my proline, nothing is really special about it. Yes, it goes back and it hooks over here. So what, who cares? I guess it's kind of small, so it can fit in those alpha helices kind of better. Whatever, right? We want to make it more advantageous. How are we going to make it more advantageous? We are going to change this to an OH. If it has an OH, then it can participate in hydrogen bonding, which in turn will highly stabilize our chains. So how am I going to do that? Well, I'm going to use prolyl hydroxylase, which is going to take an alpha ketoglutarate and change it into a succinate, which is going to remove a CO2. And in turn, I'm going to change this CH2 to a COH with an H. It's one step. That's the only thing that's happening here. What do I get out of it? I get a ton out of it. Now I have the capability of hydrogen bonding here on a very small unit, allowing them to fit together much better and be stabilized more when they're close as well. Does that make sense? Cool. Now, this is more of the alpha helices working with each other. How are we going to combine those triple alpha helices with other triple alpha helices? I'm going to do that through my lysines. So this is a lysine and this is a lysine. Well, that's weird. What's different? This one has a C double bonded to an O with an H, while this one has an NH2. We did some woo-woo magic on it and it changed it over. I'd have to look at it one more time just to make sure I'm saying the right thing, but we have this one and we have this one. They're both initially lysines on 2 separate units or 2 separate triple alpha helices that are next to each other. What's going to happen is I'm going to use lysyl hydroxylase and I'm going to literally bond them together. I'm going to remove a water or an O or an H2O, and I'm going to make a bond between this nitrogen and this carbon. Those are going to effectively hold my units together so they can't move away from each other. Yeah? Those are the 2 kind of big things about binding of our collagen. Cool. I mean, that was a lot of writing for not very much talking. Any questions? Nope. Okay, so collagen is made up of mostly glycine, 1/3 glycine. Can also be proline and lysine. Prolines are important for what? God, I'm deaf, dude. Hit me with it. Prolines are important for stabilizing the triple alpha helices through the use of what type of bond? Hydrogen bond, I heard someone say it. And that hydrogen bond is created by doing what to the proline? Adding the OH group, yep. And how am I going to add that OH group through the use of what enzyme? Prolyl hydroxylase. Perfect. Now, using prolyl hydroxylase to put an OH on the end of that carbon present on the proline will allow it to participate in hydrogen bonding, which will do what to the alpha helices? Stabilize them, yep. And now I have this very strong and stable triple alpha helical unit. How am I going to put these triple alpha helical units together? Through my lysyl hydrolase reaction, which is going to bind two lysine residues of opposing triple alpha helical units together. We can say this one is part of one and this one's part of a different one. And it's like two long arms reaching out to each other.
Say that one more time. You said lysyl hydroxylase is responsible for binding collagen to collagen, or
It's responsible for binding the alpha helical units to each other.
which are like the subunits of the collagen.
In a way, yeah. So I have these boxes, right? So let's say each one of these box has a triple helix inside of it, which would look something like okay, and then shit, I kind of fucked it up at the end, but who cares? It would kind of look something like this, right? Now, if I was to have another unit next to it, they need to attach somehow. How are they going to attach? Through this, which would be like, let's say right here. It's like linking together the units.
Is that for all alpha helices or just this specific example?
Okay, what do you mean all alpha helixes?
Because I'm assuming it's more than just the prolyl, whatever that is.
Mm-hmm.
But yeah, I'm assuming there's more than that, like more than just proline's version.
Yeah.
So is lysine, is that the one that's doing it for all of them, or is it just?
So the lysine is specifically for binding the two units together, and that's really kind of its main thing.
Oh.
The prolyl hydroxylase one, it's for just making it more stable. So you don't even have to do it on all of the prolines. Really, at the end of the day, you could do it on 3/4 of them and call it good enough.
Okay.
Also, the fact that there's other amino acids in there that are polar already, which allow for a stable alpha helix to form. It's just that the addition of these makes it even stronger. So it's reinforcing it kind of in a way.
Okay. Thank you.
Mm-hmm. All right. Well, if that's all,